During summer 2020, iOS XR 7.2.1 has been published and is now available for NCS 5500 routers. But what have you been preparing for us?
Well, we have new products, but also a lot of new features. And it will be just after the intro. iOS XR version 7.2.1 is available, and it comes packed with a lot of new features. You can see how long are the release notes this time. To talk about each of these new features and newly supported products, I contacted different experts and they recorded short sections of 2 to 3 minutes each to describe what's new, the context, the configuration, and potentially the limitations. So you will meet a lot of my coworkers in this series of videos. We split this in 4 different parts, and today we are starting the first one with segment routing and EVPN innovations, presented by Liste, Bedard, and Jiri Chaloupka. If you are interested in a specific topic, check the shortcuts in the description below. You will find links to directly jump to the feature. Okay, I'll let the true specialists make the presentation now.
Welcome, my name is Liste. I am a technical marketing engineer, part of Cisco's Mass Scale Infrastructure Group, and my job here today is to go over the recent innovations for SR that has been released in iOS XR 7.2.1. The presentation will be broken into 3 buckets, where we will start from the IGP related innovations. We'll talk about SR-PCE or Path Computation Element innovations, and lastly, SR traffic engineering. Let's move on to the first bucket. Many of you are aware, and we have been shipping FlexAlgo for quite a few releases already. In 7.2.1, we introduced the latest enhancements to FlexAlgo, where we have implemented a new FlexAlgo prefix metric sub-TLV. And what that allows me to do is to benefit from the simplicity of FlexAlgo, even in a multi-domain or multi-level environment, where by having propagation or between levels or redistribution between domains, of having a optimum end-to-end path computed by the IGP. So the combination of the leaking of the prefix with the FlexAlgo label and or the redistribution and having the FlexAlgo metric, it will allow a router in a particular process or domain, like router number 1, be able to select the optimum ABR, either 2 or 5, to reach a destination in another domain or area and remain optimum. So in this particular case, we're showing 2 processes or ISIS A or B, or 2 levels, level 2, level 1, where router number 1 is trying to reach router number 3 along the shortest path using FlexAlgo 128. And FlexAlgo 128 in this case may be minimizing the delay. So the key job here is to let router 1 pick the right ABR. With the metrics which are shown on the slide, which are the link delay metrics, the optimum ABR to choose is to go via 6, directly connected router, onto my way of ABR number 5. And with this router, I can achieve the lowest end-to-end delay, 8 plus 9 plus 11. And that being less, that if I would gone via 2, would have been 10 plus 23. The FlexAlgo metric and the extension with the sub-TLV, we can now compute paths that are optimum end-to-end, that they are simple, that they are very efficient. Only one label will allow me to go between domains, and this is a iOS XR 7.2.1 functionality. From the configuration perspective, you will just enable the CLI shown under your FlexAlgo configuration for the router, for the routers in your ISIS process for FlexAlgo 128 as an example. Moving on to the second feature, we're going to talk about the rounding of mean delay values. Already for a few releases, we have been allowing our routers in an MPLS network to measure the delay on the links and then propagating that delay into the IGP as a link property. But what actually comes natural is to realize, well, there are many cases where I do want to minimize the path, for example, minimizing the delay from source to destination. But in some cases, I have paths that are very close to each other from the delay perspective. So in this case, if I want to minimize the delay from 0 to 9, I go via 5 and 6. And my cumulative delay will be 20 plus 29 plus 20. But if I were to go over the top, the difference is only 2 microseconds. So I would really like to stay IP friendly, ECMP aware, and can I realize a end-to-end path minimizing the delay that exposes other ECMPs and in a much richer path. So in this case, we configure what we call the latency normalization, and now by normalizing the delay on the links, like for example the link between 1 and 2, and normalizing the delay between 5 and 6, the normalized delay in this case, based on the configuration that I show, will be the value of 33, and therefore router number 0 will be able to have an ECMP rich path minimizing delay from 0 to 9. The third feature is one that introduces the latest type of protection for TI-LFA. As you're aware, we have been shipping TI-LFA in Cisco's implementation for ISIS and OSPF with a very rich type of protection like link protection, node protection, local SRLG protection. And now what we're doing for OSPF, we are introducing weighted remote SRLG protection. So in this case, you have a PLR like router number 2 that is trying to protect traffic on an interface, for example, interface 0 connecting to router number 5. But it turns out that interface 0 on router number 2 and interface 0 on router number 4 are in the same conduit. Maybe it's on the same pipe on the street. So they are assigned to the same SRLG. So the idea is to give a notion and give awareness on the PLR to avoid using a remote link that happens to be on the same SRLG as a protected resource, like in this case, interface 0 on router number 2. So when you do that, you realize a very rich backup path where, as shown by the segmented line, router number 2 will actually not send the traffic on the link between 4 and 7, but rather take the path shown in the violet dotted line. So yet again, one more flavor of TI-LFA to build a family of different protection types. In 7.2.1, we are releasing this last flavor of protection type for OSPF. This protection type has been shipping for ISIS for quite a few releases already. And last, we're going to talk about how can we leverage Jiri as an outgoing interface for a TI-LFA backup path. Many deployments out there actually rely on multi-domain or multi-level environments where it happens that the ABRs or the ASBRs are not directly connected. So if you take a look at the picture that we have on the screen, routers 2 and 3 are my ABRs. In this case, I'm showing a multi-level design. And the idea is obviously, of course, to provide TI-LFA within each level. And because these two ABRs cannot be connected directly to each other, the ability for the IGP to pre-compute a backup path within the level is now compromised. So the way how we address this is to allow a Jiri tunnel, in this case shown on the screen, to be able to use as an interface within that level. So therefore, the IGP can compute a backup path that leverages that low logical interface. Of course, if I want to use the Jiri tunnel as an interface to be leveraged by the level 1, then I want the path of that Jiri tunnel to traverse the interfaces on my level 2. And this is what I show with the thinner dotted line. So yet again, the idea is to provide a very rich multi-level, multi-domain process designed. And yet again, even in situations where you cannot connect the ABRs, which is typically a non-technical but rather a fact, we can still allow the IGP to pre-compute backup path within each level and then take care of failures like the failure between 2 and 5 or the failure between 7 and 8 and have pre-computed backup path that will leverage the Jiri tunnel between the two ABRs. Well, now we're moving on to SR-PCE features that are shipping with iOS XR 7.2.1. So the first feature we're going to cover is the Flex Algo-aware path computation. This is a new functionality where we allow the operator to enjoy the simplicity and the efficiency of an optimal end-to-end path that is encoded with the Flex Algo labels when you are using, in fact, a multi-domain design. We have a two processes, the blue and the red process, where we're going to be using Flex Algo instances, And the objective of this is to actually be able to compute an end-to-end multi-domain path from 0 to 9 that adheres to the definition of the flex algo, and therefore it will be optimized for the criteria given by the flex algo. So let's look at the example in a bit more detail. So my two domains, as I said before, they're both running a common flex algo. The flex algo may be defined to, in this example, to minimize the delay. The delay on the links is shown on the slides. And we can see from the service perspective, router number 9 is advertising a prefix 2/8 via next hop 9 with an intention to minimize the delay. And that BGP update arrives on router number 0. So the gist of this new behavior on our Flex Algo-aware PCE is that now a PCC like device number 0 is going to be capable of saying, well, I would like to have a path that goes to 9 adhering to the Flex Algo 128. So you can see on step number 1, the router will issue a request for a path to 9 following Flex Algo 128. And what the PCE will do in this case, after having learned the Flex Algo definition and the Flex Algo prefix sits and who is a member of a particular Flex Algo, the PCE will return a label stack of 2 labels. In this case, is the optimum ABR, minimizing the delay. In this case, will be ABR router number 5 with the label 16805, and then subsequently the destination PCC router number 9 with the Flex Algo label of 16809. Key highlight here is I'm building a multi-domain path by using Flex Algo. What the routers will do is they will require only a single per domain to reach the next ABR. So highly efficient and very simple path computation done on the PCE, and highly efficient for the label stack on the PCC. The second feature is, we call it the SRTE to BGP-LU interworking. And how the name describes, we're trying to provide, yet again, a new functionality on the SR-PCE that we will allow the PCE to compute a path for a local client, like router number A in this green domain, where router number A is running on a segment routing enabled domain and no BGP-LU. However, this domain is connecting to a legacy already existing core with BGP-LU, and as well to destination access domains that are also running BGP-LU. So the idea here is to simplify my green domain, which is only running plain SR, having an SR-PCE where if the router number A needs to send traffic to router number Z on the far right, it will ask the PCE, can you please give me a path to Z? And the PCE will be able to compute a path, basically asking its client to go to the ASBR of the domain, router X1, with a label stack that when it arrives on X1, it will be cross-connected into the label cross-connect entry that will take me across my existing BGP-LU LSP in red. So the idea is to make the SR-PCE smart to return a label stack to A such that when that will lead the traffic to the ASBR, and the innermost label on the SR policy will be one that will allow the cross-connect to be made onto a BGP-LU LSP. The last feature in this bucket we're going to talk is the support for MPLS-TE LSP on Cisco's SR-PCE. Cisco's SR-PCE has been around already for quite a few years, and it actually began its journey as a SRTE, primarily PCE. We have now allowed the SR-PCE to also be able to perform path computation for legacy MPLS-TE, RSVP-TE LSPs. So what you can see now is that the SR-PCE continues to learn the topology from BGP-LS. It can use an application like Cisco Crosswalk Optimization Engine to display such topology. It communicates via PCEP with the head ends in the network, but now the network is MPLS-TE, RSVP-TE. The idea here is for customers who do require a PCE, in this case, to perform a centralized path computation that is required for the use case. And this is very commonly seen in cases where, for example, we want to perform a disjoint path computation for 2 LSPs on 2 different head ends. So I have an RSVP-TE tunnel green, RSVP-TE tunnel red. I need them to be disjointed. Neither head end can perform the computation. The SR-PCE can, and based on PSEP and the support that has been added to the SR-PCE, we can compute the path and return the path to the head ends so that the use case can be realized. Last, we cover the innovations related to SR traffic engineering in iOS XR 7.2.1. In particular, we'll focus our attention in the PerFlow ODN, on-demand next hop, and PerFlow automated steering. And my coworker Jiri will be presenting the innovations related to EVPN over SRTE in this release. The objective is to take our intent-based automated story to the next level. For those of you following automated steering, the ability to steer traffic automatically for a particular service or for a particular destination is something that we have been shipping for a while. But now we're allowing us to take it to the level of the PerFlow. For that, we introduce a new concept called the PerFlow policy, or PFP, PerFlow SR policy. The idea now here is that you could have a PerFlow policy such as the blue item I show in router number 6, where you could have not just one way to get to a particular endpoint, but you can actually have multiple ways to get to it. So the notion is, if I receive a prefix from the network that is coming in with an intent that requires PerFlow steering, in this case I'm gonna semantically describe that intent with a color blue. And for example, I have a BGP route for prefix T via node 4 with color blue. The Egress router number 6 in the lower left hand side will be able to map according to the classification criteria I have configured on the interface to the left of 6 and identify different applications. All of them are sending traffic to the same prefix. According to the classification criteria, I want to have some of the traffic following a path that minimizes the IGP cost, and some of the traffic, for example, that is more latency sensitive, that follows a path minimizing the delay to the Egress PE number 4. And that is the gist of the value and the need for doing PerFlow. Pictorially, you can see this again with a prefix that can be advertised by the network, prefix 3/8, where you have a flow to 3/8 that can just follow the min IGP path, but maybe you have another flow to the same prefix where you need to minimize the delay to the destination. Again, what we have here is we have one destination prefix 3/8 and different intents or different flows. So therefore, the need for the PerFlow automated steering. For those of you who like to see the CLI constructs, here we have a CLI slide on how you would configure the on-demand template for a PFP. So in this case, it is the same technology we have been using for ODN before, but now I can define a color 100 or color blue that in this case, instead of being mapped to a single path, is going to be mapped to an array of paths. So I have a forward class in iOS XR, which identifies is going to be used as the identity of a flow, and then it is going to be tied to another child policy with a color 10 or color 20 that will take me to the intended destination with the intended SLA. In my case, color 10 might be the path that minimizes the IGP, and color 20 is the one that minimizes the delay. With these ODN templates, you do not have to configure the policies. You will just, the ODN templates will be triggered once the BGP route arrives. You can also have the PerFlow policy be configured manually, where you define the policy with color blue, color 100, and a particular endpoint like 1.1.4, and then you can configure the PerFlow characteristics like I went over in the previous case, but this is for a manual PerFlow policy, and then you can also have your manual children policies underneath. In this case, I show the child policy for low delay. Please make sure to follow us in our external segment routing-routing.net website, where you can find the latest news related to segment routing, whether it is conferences, demonstrations, ETF or standard activities, and the latest news overall for SR. Thank you.
Hi, my name is Phil Bedard. I'm a principal engineer here at Cisco, and I'm going to talk a bit about two features that are related that we added to 7.2.1 around Egress peer engineering. And those are the addition of the manual EP SID configuration, and also the addition of what we call a peer set SID. Previously, we had something called a peer adjacency SID and a peer node SID that are used to direct traffic to specific BGP peer links or BGP peers across multiple links. What we didn't have was the ability to manually configure those SIDs. Those SIDs were dynamically allocated by the system. Adding manual configuration allows us to keep those manual adjacency SIDs and peer node SIDs, as well as the new peer set SIDs across reboots. They're persistent. And what that really allows me to do is define a SR policy on an Egress node and keep the SID the same across reboots. It never changes. So I don't necessarily need a dynamic controller to instantiate those policies anymore. I can manually configure those. The peer set SID is an addition that we've added that allows you to combine adjacency SIDs and node SIDs into a set of links or a set of nodes that are addressed with a single SID. And it's really a powerful way, as you see in the example here, of being able to balance traffic between multiple egress peers by addressing that single peer set SID in the SID list. One more example of how we would use the peer set SID. In this case, I have 3 egress, 1001, 1002, 1003. And normally I may take just a single BGP path to one of those peers. But using SR and using the peer set SID, I can use a single SID as the last SID in that SID list in order to send traffic and load balance traffic across all 3 of those connections. So as you can see, I build that SID list on the Egress node with the Egress node and that Egress EPE peer set SID. And the Egress node will then use normal per flow load balancing to load balance traffic to all those 3 destinations, which allows me a very easy way to do that type of traffic engineering without having to manipulate things like BGP best paths or BGP attributes to do so. When we look at the configuration, it's actually quite simple. The configuration exists within the BGP router context. And all I really do is kind of globally within BGP define what my different peer sets are. I give that an identifier and then an SR index. So where you see index, that's really a segment routing local block index. So I'll utilize the local blocks plus the index, and that will be the SID that I'm using to address that specific peer set. And then when I define different neighbors, I define a peer node SID, and now I can do that manually. But then I also add a peer set identifier to combine those into the same peer set. So as you can see, I can use this mix of both adjacencies and node SIDs and add those to a specific set to address all of those egress links for traffic that is using that egress node and that peer set identifier.
Hello everyone, my name is Chaloupka, and I will talk about EVPN related features in a 7.2.1 iOS 6R release. You can see here that I have EVPN and EVPN VPWS on-demand next hop, which is basically closing our gap on the BGP side to provide on-demand hex hop, basically to get all the BGP services over the programmable transport. What we are doing with the EVPN and EVPN VPWS, we are coloring the route type 1, and for EVPN we are covering also the route type 3, and the color specifies the particular SLA. You can see the configuration on the R38, where I have a route policy where basically I'm saying when I'm advertising the EVPN route type 1 or I'm advertising EVPN route type 3, I want to set the extended community color. Then I have an extended community color where I decided to use the value 100, and then there is only a route policy export, basically attaching the route policy to the exporting over the BGP. Then on the left side, you can see very simple configuration for the segment routing. You can see that I have on-demand color 100, and I just specify what I want to get from the transport when I'm receiving the color 100. Basically, I'm specifying the SLA. Here, for this basic example, I'm just saying, okay, I want to follow the IGP metric. So basically, I will get the path based on the IGP metric. I can verify that particular routes are going through the particular traffic engineering policy. So first, the BGP, you can see that I'm receiving this route type 1 and route type 3 with the color 100. You can see the tag color 100, and then I can go and I can see the show segment routing traffic engineering policy, where this particular traffic engineering policy is automatically instantiated and is basically pointing to the node 38, and you can see that it's up. The next one is EVPN E3 with the RT constraint. This is a very basic BGP behavior when we are manipulating with the route targets. So we can do the same for the L3 VPN, but we need to get some additional stuff for L2, especially when we are doing multi-homing. So first, what we want to achieve with the EVPN E3. In this case, any device which is marked as a root can talk to anyone else in the network. But leaf can talk just to the root, but leaf cannot talk to another leaf. So in our example, H1, H2, H3 can talk to H4, but H1, H2, and H3, they cannot talk to each other. You can see that basically we have two sets of the route targets. I have a blue one, which is one column 1000, which is on the root side. So you can see that the root is importing and exporting this particular route target, because again, a root can talk to anyone. And then I have a green one where there is a route target import 1 column 100, and this particular route target is exporting from the leaf. And you can see on the leaf side that leaf is exporting this green one and importing only the blue one. It's very basic behavior, as I mentioned. But what we have here is additional configuration for the E3 on the leaf side. I have a RT leaf. This is important there to basically provide the MAC address synchronization for the dual home host. You can see that H1 and H3 are dual home. So basically, leaf 1 and leaf 2, they have to synchronize the MAC address of H1, and leaf 3 and leaf 4, they have to synchronize the MAC address for the H3. So basically with this, we will advertise additional information over the BGP, and this synchronization can happen. There is one more additional configuration when I want to prevent like the local talk over the bridge domain, for example, between H1 and H2 over the leaf 2. I'm specifying the split horizon group on the interfaces. So basically, locally, I'm preventing the communication between H1 and H2. The last one, which I'm bringing here for a 721, is the MAC freeze auto recovery mechanism. MAC freeze mechanism is there to protect EVPN and BGP control plane, and we have this feature there for some time. But what was missing is basically to provide some auto recovery mechanism. So here I have a new CLI, which is the reset freeze count interval. This will help to basically recover from permanent frozen the MAC address. So that's all from my side at this moment. If you will want to see more information and you will want to get more information about the EVPN, please follow us on e-vpn.io, and you will be always up to date. Thank you.
Thanks a lot to Jose Liste, Phil Bedard, and Jiri Chaloupka, who gracefully gave of their time to prepare these presentations. I hope you learned a lot. In the next episode, we'll talk about the new products we introduced in 721, the new optics supported, and then we will cover Wi-Fi, QoS, load balancing, SCL, and security innovations. As usual, you can ask questions in the comment section. See you in the next one.